Hi, I'm Federico, and I'm excited to present our work on scan path modeling today. Let's jump right in. When viewing a scene, your eyes actively explore it through scan paths, sequences of rapid movements, and fixations. And as this classic image shows, researchers have long known that this process is not random. Where we look and when is a sequential decision making process, and scan paths are a direct, real time window into its cognitive aspects. Understanding this is essential to fields ranging from neuroscience to computer vision. Here, we're specifically interested in the modeling aspect, both predicting and understanding sequences of fixations. This brings us to a fundamental trade off in building models for scientific phenomena, which we call the Pareto front of modeling. Essentially, all models are on a spectrum. On one end of the spectrum, you have high performance, more black box models, like in our case, deep gaze. They take a data driven approach and are great at prediction without explicitly modeling underlying mechanisms. On the other, you have mechanistic models built from small sets of interpretable components, like scene walk, which usually directly reflect scientific theories, but do not predict as well. So, how can we improve them? Where are they losing performance? In static spatial saliency, researchers compare to empirical fixation densities to pinpoint systematic model errors. In scan path prediction, this is not as easy. When predicting the sequences of fixations in a scan path, we are predicting each fixation given its history. For this distribution, we typically have only the actual next fixation as a sample. Therefore, we cannot compare against a simple non-parametric model to determine whether a poorly predicted fixation was just inherently unlikely or whether the model failed to capture a pattern. Here is where high performing models can help us by acting as a learnable stand in for the unknown true distribution. By comparing a model's prediction to the deep gaze prediction, we can decide in which case a subsequent fixation could have been predicted much better than it is. And note that we're not saying deep gaze is a perfect model for scan paths, just the best proxy we currently have for human predictability. This concept is at the heart of our approach. We start with human fixation data. We feed this data into both models. Then, at the level of individual fixations, we compare their predictions. We are looking for what we call controversial fixations. These are the key. These are fixations that deep gaze predicts very well, meaning that they are predictable, but that scene walk fails to capture. We use them as entry points for analysis. We find patterns in these failures and then propose and validate new mechanisms that could explain them. Finally, we integrate these back into scene walk. This loops allows us to use black box models as a scientific instrument, translating predictive power into testable cognitive hypotheses. So the key of all this are controversial fixations. And when looking at them, the most important finding was that they weren't random. We found that most of them fell into just four clear interpretable categories. These pointed us directly to the specific missing mechanisms we needed to add to our model. For now, let's just focus on one of these, the early saccades, and walk through our process. Our clue was that scene walk was consistently too uncertain on the first few fixations compared to deep gaze. So we analyzed the data and confirmed that humans and deep gaze are actually highly confident and focus on saliency early in a trial. So we proposed a mechanism, time dependent temperature scaling, modeled as an exponential decay. This forces the model to be deterministic early on and explore more later. Finally, we validated it, and our new model now matches deep gaze's performance curve on those early fixation, and crucially, solves the original controversial example. We applied the same cycle to derive mechanisms for saccadic momentum and cardinal biases. And so, what was the combined impact of these three new mechanisms? Well, this is our final result on the MIT dataset. On the left, you see the original scene walk, and on the right, scene walk X, the new model. With just three simple interpretable additions, we doubled the model's performance, closing over half of the total performance gap to deep gaze. This sets a new state of the art for mechanistic scan path prediction. And crucially, this wasn't just a quirk of one dataset. We validated this on other datasets, including Demons and Coco Freeview, and we consistently have the remaining explanatory gap. This proves that the gap between interpretable models and black box models is not unbridgeable. We can use deep learning models as scientific tools, in this case, to find the missing pieces and build better, high performing, and understandable models of cognitive phenomena. So with that, I'd like to say thank you and point you to the paper and code for our project.